I'm a scientist, I'm an active scientist, and I think about these questions, and at that same time I spend half my time engaging with people around the world and communities and just learning how they think about science. And in this respect, I mean, we spend a lot of time building tools to make science accessible, but I hadn't realized this, that what we were really doing is building communities around the world that are equally passionate about science, but now have something in common. Around these tools, we are coalescing communities. So what I'm most passionate about at this moment is this scientific community that we are trying to mentor that spans every corner of this world, that have something in common, which is these scientific tools, but their curiosity is far beyond my imagination. I mean, people in our community have asked questions that I would have never imagined, in systems that I have never experienced or seen, and in circumstances that I cannot imagine. So I think, I'm most excited about the human spirit. So although when I started, I was not so optimistic, but I'm very optimistic now. We have to give the means for people to think, and we will come over, all the problems that we are leaving for our kids. So, although there are big problems, we have plenty in the young generation to tackle them, but we have to support them.
Let me begin by saying how honored I am to be here, and especially for an inaugural event. This is going to be very informal, so come up any point of time, interrupt me at any moment if you will. And I have little tools and toys. You'll realize why toys are so important in this context out here in the front. One of the threads of this is, what Alejandro described, is these chance moments lead to many things sometimes that I find very unpredictable. So my real hope is that we don't stop here. This turns into a conversation that we get to take forward, both in communities around the world, but communities right here. Okay, so to begin the story, I have to start with people. You've already realized, looking at this, I'm a scatterbrain. I think about many different things, and this is a little snapshot of how I'm thinking. And most important in this little cartoon are the people, the young people that I actually get a chance to work with. And many a times I never end up finishing my talks. So this is the acknowledgement slide to begin with. And we really have to acknowledge people we get a chance to work with, because I think they inspire me in many ways, and I inspire them in many ways. And this mutual relationship really takes us places that we never thought existed. They are not just cartoons, they're real people. But one of the things that I will try to bring in today's conversation is not just communities of scientists that we all get a chance to work with in our local neighborhood, but I get a chance to interact with communities around the world. And I'll share certain examples of how those communities have taken the type of science that we do in places that I had not imagined, and for some of them actually brought them into the fold of science, which is really the whole point of this conversation. So let's begin with a journey of discovery. And I'll try to give enough examples to really share with you that science belongs in everyday's life. And I will begin with a challenge, the challenge for all of you, which is, let's imagine a school. Close your eyes and imagine your school. What does it look like? And do this for a moment, because you'll be reminded of your teachers and the moments that you grew up. And now open your eyes. And the irony of that world is that this is what an average school looks like. This is a picture that I took in Ghana, and you might say, wait a second, it actually does have a roof, but roof does not make a school. And there is nothing to inspire creativity of talent that exists on this planet. And when you do the numbers, you realize there are roughly 2 billion kids on this planet. and 1 billion of them currently live under standards that would be qualified actually as poverty standards. That's half of the entire creative workforce that we are about to unleash into this world. This has nothing to do with the picture being in Ghana or anywhere else. This is not about, the talk is not about developed versus developing countries. It's about haves and have-nots. And you have to really realize that we need to change access of science at an early stage. Now, I make connections between science education and health. So I'm not going to let you imagine this, because this is really hard to imagine, is what does the average hospital look like around the world? This is, again, another picture that I ended up taking in Ghana. That's a complete accident. This is a bus stop that, there was a bus stop that essentially a van comes by and it happens to have or not have a doctor. And you have a kid that's sitting with an infectious disease and you're anxious, and this bus comes once a week and you might or might not see a doctor. Again, if you look at the statistics around the world, roughly around 1 billion people, again, live with absolutely no access to roads or infrastructure or any electricity, and for that matter, no real access to healthcare. And I think some of these extreme examples try, at least personally for me, push me into thinking about we have to come up with extreme solutions for extreme problems. And to really drive this matter home, to have you understand why biomedical science is so important, and we still have battles to fight. We really haven't won this in any way, is another picture that I took in Uganda. Now, this picture to me is horrific in many ways, and it's my nightmare playing over and over again. This is a pregnant mother that I met and these kids that I played with. And then when I was walking away, I snapped a picture, and I was walking through having a conversation with my translator who was with me. And he asked me a simple question. Did you realize what these kids were sitting on? And of course, in a few moments, you understand these are graveyards of their brothers and sisters. Malaria by itself, for example, and this is only one of uncountable number of diseases where we do actually have lots of solutions, but they don't propagate to the people who need them the most, take an incredible toll on human life. And to me, this situation needs to change. Another reason why our healthcare solutions need to go and be accessible to the broadest group of people. Now, to the positive side of this story, which is everybody here did hear about Ebola. And many of you actually, what is incredible, also heard about people like Alicia, who's a healthcare worker in Liberia. The only reason we're not talking about Ebola in our current statistics and conversations is because people like Alicia went out to the places where diseases arise and fought them. She's a community health worker. She has essentially a high school degree, but she carries her passion for bringing solutions to people, and with the little bit of tools that she has, you can notice this, she's wearing a backpack, enables the kinds of solutions that drive to the last mile. And one of the contexts that I'll share, Alicia is not alone. There's an incredible number of people that I get a chance to meet who get trained and work out in the field as health workers. But there is a flip side to that story, which is, this is Alex. I met him again in Tororo, and I had an incredible conversation. Alex knows more biology than I ever will. He really spent time in microbiology labs for 6 years, got trained to be an expert lab technician, and gets shipped to this location in Tororo, and I asked him, show me your lab, and this is his lab bench. He said, when the patients are not on the bed, I get to use these beds as a lab bench, and you can really see what tools he has to bring solutions to people. So I think this idea of access to scientific solutions, both in health and education, bring me to how I personally define frugal science. This idea that knowledge is really available. Any of you could Google many things at this very moment while I'm talking, and knowledge will be free very soon. As access to information becomes more and more broadly available, we have a challenge in science to bring the experience of science to people. And how do we actually do that? What do I really mean by the context of making affordable scientific tools to bring the experience of science. Today we'll get a chance to very briefly touch upon a few ideas of what I mean by that. I'll spend some time on educational tools, sometimes on medical tools, but before I start, I am going to do a demo. And since many of you decided to sit so far away from me, we're going, can I know your name?
Ashley.
Ashley is the brave enough to be sitting right up front. And fortunately or unfortunately for Ashley, I am going to expose her to a certain sound, which many of you will hear. I have a piece of Scotch tape here. You know, everybody's used Scotch tapes here. And hear very carefully when I do this, you're going to hear a screeching, annoying sound. And let's really come close to Ashley. And did you all hear that? That screeching sound. At this very moment, we have exposed Ashley to X-rays. And I mean X-rays, like the X-rays when you go get your dental X-ray as an exam. Now you might think, you know, I'm a little bit lunatic or crazy. It turns out a single piece of adhesive, when pulled at a certain velocity, actually emits soft X-rays. If we were in a dark room, you would have seen a flash of light emerge from this little point. And this is the context of what I really mean by frugal science. This was in the 50s, a group of Russian physicists wrote about this phenomena, of course, in Russian. Many people didn't read it. In the late 2000, a physicist at UCLA repeated the experiment, demonstrated that this actually emits X-rays. We have some ideas of how that works. But more crucially, actually showed that you could use a tool like this to perform a real X-ray on a patient. And this is what I mean by frugal science, that the idea that solutions sometimes come from places absolutely far away from what we were imagining. And suddenly, now there is a company actually building adhesive-based X-ray sources trying to bring X-ray imaging to places around the world in a completely different light. And to me, the sense of surprise that comes in solutions like this is also the intellectual joy, that when you stumble upon these gems, it really teaches you things and ways of thinking about science that you don't often think about. Sorry about the exposure. It's low enough that if you take flights regularly, it doesn't affect anybody. And, you've been pulling Scotch tapes all the time, so. But the point that at least I want to make in this is it's not about the tools. It's mostly about the community. So what I would like to communicate is just this understanding that if we get a chance to enable communities globally to experience an access of science, remarkable outcomes occur that we don't have a chance to predict. The way we do this is to spend time in the field. So over the years, this is Mr. Johnson. He has been teaching pathology in Uganda for the last 30 years. I met him for the first time. I shared the Foldscope. I showed him, and he said, oh, wait a second. You're telling me you can do diagnosis under a tree. And I really take that to heart when I mean that when you have literally nothing, how do you really create genuine scientific data, genuine scientific experiences quite under a tree? And over the years, these communities have taught us quite a lot. And what I'm going to try to do is, because we're going to run out of time, really share snippets of solutions. And you will see in this madness, there is a method. They span all the way from being able to map ecological diversity of diseases, to be able to build tools to truly bring analytical diagnostics tools out in the field. And in the very end, I'll talk about Foldscope in being able to bring that experience of microscopy that David talked about. So let's start with mosquitoes. Do you have mosquitoes in Kansas City? That's good to start with, because sometimes I'm talking to an audience who've never actually experienced. Have you been bitten to bits by mosquitoes before? So you understand my pain. And you all know, I don't have to explain this, this little creature, although it has wonderful biology, and I love it for that, kills the most number of people on this planet. Combined, all wars and everything combined, this little thing has killed more people. Now you might ask, how do we fight our enemy? You fight your enemy to know, first of all, where the enemy is. So let me ask you, There are tons and tons of mosquitoes that are out there. How many species of mosquitoes are out there? And if somebody who actually works on mosquitoes, don't give out the answer. But I'm just curious, from your experience, how many species of mosquitoes might be around? You can shout out. This is very informal. Anything that comes to mind. Any numbers? 2,000. 2,000? Anybody else? Everybody agrees it's 2,000? It's hundreds at least. There's roughly around 3,500 species of mosquitoes. Not all of them carry diseases. Only between 20 to 40 species actually carry pathogens. But one of the challenges that we have when the slide shows up here is you'll realize being able to identify these mosquitoes out in the field is quite difficult even for a trained medical entomologist. We started thinking about this problem way before Zika became so important. I'll ask you this. Zika spread, everybody's heard of Zika. Spread to millions of people, 40 different countries. The Brazilian army decided to go out there and really see which mosquito is transmitting. They spent 6 months collecting mosquitoes in the field. I'm curious, can you number, how many number of positive mosquitoes that they found that were infected with Zika when we have millions of patients infected? What does that number you can shout out an answer. How many mosquitoes do you think might have been positive of Zika? This is not a quiz. You could be happy to be wrong. Yes? 100. Actually, 4. It tells you how remarkably little we know about ecosystems. Again, going back to basic science is the fact that the worst enemy that we have, we know so little about the secret life of this animal. We started thinking about this because not only do we not understand where the diseases are, we actually also don't understand where the mosquitoes are. This is the latest Aedes aegypti map, a mosquito that causes dengue, chikungunya, Zika, and many other diseases. And this is generated computationally, and the total number of data points in the entire continent of Africa is 575. This is incredible effort, but at that same time, this map is not a map of mosquitoes, it's a map of entomologists. Because the people who are out there, the scientists, we're so sparse that this is what we can do in being able to map these problems. How do I do this? When I go out to the field collecting mosquitoes, this is a beautiful image taken by Adam Nadel. I roll up my sleeves because you want to get mosquitoes that bite humans. You are the bait. It's actually quite unethical to be able to do this. You roll up your sleeves and you sit there and you let a mosquito sit on you. And right before it pierces your skin, you try to catch it. I can be on drugs and things like that to avoid some of these diseases. But one of the challenges is for something like dengue, if you're going to sample, we have no solutions. So it's quite dangerous to be able to sample this. And some of you who remember Ronald Ross, who got the Nobel Prize for actually finding that mosquitoes carry malaria, actually used the same techniques. What do we do when we carry lots of mosquitoes? Here's my favorite picture of a biologist. He has a fancy trap that allows you to catch tons of mosquitoes. Here's a bucket full of mosquitoes for you. And now what? You go through one at a time under a microscope, speciating and identifying them. So we built 2 tools, and I'll only get a chance to talk about one, but we built tools that anybody out there now can really do molecular sampling of single mosquito bites. And then I'll tell you a puzzle of how we're trying to engage all of you, both scientists and non-scientists and kids around the world, to tackle this problem. And for that, I have to play an orchestra. And I would like you to predict, what are you listening at? So let's play this audio for a second. What do you think this is? But pay attention to what's happening. It would be very hard if I could actually train an orchestra of mosquitoes to play this. So I made this, but for a very scientific reason. You can, and some of you who have a musical ear, you can identify these notes. These mosquitoes are playing notes, and that's because this is an orchestra. I took 20 species of mosquitoes that carry human pathogens, and the reason you can differentiate them, this is the fun fun part, I like that, is because different species of mosquitoes actually create different frequencies of sound. So mosquito species happen to have signatures. Now, why is this interesting and why fundamental biology is so important for applied sciences is this was discovered fairly recently, that not only, this is a female mosquito flying and a male chasing her. Many mosquitoes mate in flight. That female is creating an acoustic signal that this male with his big mustaches is actually listening to. A lesson for most male in the audience, you should listen. Because the female is not only producing a signal, she's modulating it very so slightly, and then the male has to actually catch up with that frequency, and if it doesn't, it's not a good mate. So mosquito species have evolved in these ways to create these acoustic signals that are primarily coming from flapping. So that frequency of sound that you hear is actually correlated to the flapping frequency of that mosquito. And we made a realization that tools like this that you and I carry around the world, and not just these fancy little tools, but even flip phones, carry acoustic sensors that are sensitive enough to actually capture that. So we created this tool we call a Buzz, which is an idea of Shazam for mosquitoes. How many of you have used Shazam? So you all know what I'm talking about. Could we really deliver a tool around the world that any little kid could pick out their phone, record something, upload it, and using machine learning, we actually identify these mosquitoes? I have very little time, so I'm going to go a little bit faster. This is a signature for Anopheles scampi. And these buzzes you might not like, but are actually really fun. And from that, there is a specific band of frequency that I pick. This is data recorded with a cell phone that allows me to give a specific signature, not just the peak frequency, but also the distribution of these. We do this for species around the world. This happens to be the largest acoustic database of mosquito species. We're at 20 species that carry pathogens, and we collected this with entomologists around the world, but this becomes a golden map that then we can use. When you upload your data, we can tell you what species of mosquito that was. This was not done with a fancy phone. This was actually done with a graduate student who happened to have a 10-year-old flip phone, which cost her $10 when she bought it. I am sort of sad that the battery on this phone is dying, because these have become relics on eBay, and I can't find these old phones. Also, when we go out in the field, there are 5 billion of these. 5 billion. So we have a tool that if even 1 or 0.1% of community started to engage, we would build the world's real-time, the most dense mosquito maps, and then you could put resources in those settings to actually fight these diseases. We exactly did that for Madagascar. We're starting to start programs around the world and release some of these tools, and we demonstrated that many of these tools actually work far better than when even entomologists who partially go and sample these mosquitoes. So anybody who's interested, go to buzz.stanford.edu and you can start collecting data. I'm going to transition to a couple other tools. The next one comes from the context of diagnostics, and it comes from an experience in Uganda where while we were doing some of our microscopy field test, I was at a field site and I saw a field health center right here where they used a centrifuge as a doorstop. So how many of you know what a centrifuge is? Most of you, you all use centrifuges, but it's a very interesting use to use it as a doorstop. And when I asked, they said, we haven't had electricity for the last 5 years. So what good is this piece of junk? And that sort of sparked an idea. Now, centrifuges are very important from a biomedical, and especially in a diagnostics perspective. Detecting diseases in samples is like searching for a needle in a haystack. But imagine if, because the needle has a heavier density, if you could spin the haystack, you could pull out the needle, and then you don't have to search in the haystack. You really look where this needle should be. The same idea applies for diseases. And while coming back, I started thinking about toys. You will start realizing that there is a little theme to this. And the toy that I started thinking about is, how many of you have played with what is called a button on a string, or a run run? So that tells the age of this group, the people who raise hands. I find it ironic how come fidget spinners can be picked up in high schools, but these things haven't. So for the young audience who haven't, take a button when you go back home, put 2 threads, and you formed a string, and then I am winding it, and when I push and pull, you notice something interesting, that this object starts spinning. Now I'm going to go higher. Now this object is very simple. I mean, it's a string and a couple of things, but it's actually spinning incredibly fast. And what I find remarkable about when we started thinking about this, I started digging in the history of this object. This object happens to be the oldest known toy in the history of mankind. 5,000 years ago, we found relics of this object in all cultures, Inuit cultures. Greeks used to use this as a musical instrument, and in every culture it's been described and played with, but nobody asked a question, how does this work? And by asking that question, we were able to do something. This is not the only equation in my talk. By asking this question how it works, you start to understand how a simple object is actually remarkably complex. To really understand this, you really have to understand you're injecting energy by pushing this in and out. That leads to these twists. There is an air drag on this. That's what's creating this sound. And what's really surprising is some of you who are up close, and you should all sit up close, you can see that the string is actually supercoiling. The idea of supercoiling is a coil of a coil. We use the exact same equation that we use to understand supercoiling in DNA, but now plugging that in, it allows us to understand the mechanics of this tool. And with that, when we re-engineer and design this tool, we now currently hold the world record for fastest spinning object with human power. And anybody wants to guess what that number is? How many rotations per minute could you go when I'm pushing this? People who have read the paper, you shouldn't shout out, but anybody else? 5,000 RPM? Yeah, I'm happy that you have some confidence in us. Anybody else?
Look at the graph.
Yeah. 120,000 RPM. Your yo-yo, a very good yo-yo throw is around 4,000 RPM. But you really have to learn a yo-yo, and we actually did a lot of math for yo-yos. Eventually we arrived at this. Now, the reason I made a big deal about this number and really understanding the science behind it, the basic science of this toy, is that we get to build a centrifuge using this, which competes with this object. The effective RPM leads to 30,000 G forces, and within 90 seconds, I can separate out plasma, pure plasma, from a capillary of a blood. Now, why is that important? There are 3 billion people on this planet who need an anemia test every year. Many of them are pregnant women, and this ratio of plasma to packed volume actually gives you whether you're anemic or not. Now, if you've heard of rapid diagnostic tests, which are these pregnancy-type tests but are used for many diseases, if you do that with plasma, your sensitivity and specificity increases, so we get to do that. But more interestingly, if you take a little more time, say 5 to 10 minutes, I can pull out a single infected malaria blood cell out of a sample and really image that using some of our microscopy tools, so you really push the bounds of what you can do out in the field. Now, I glow when I think about bringing many of these tools out to the field, and this is what that looks like. This is a village chief in Madagascar. The only woman in this room is the healthcare worker. This village is 12 hours walking distance from any roads or any infrastructure, and this is the smile that we try to create. Unless the chief agrees, we cannot proceed to do some of our clinical tests. But one of the values of this is, you know, when you make and work on toys and you bring them out, you're a little bit afraid that you get out there and say, you know, what is that? Give me the next shiny object. But what I realize whenever I travel and bring these tools to people, they understand the value. They understand because this is the person whose kids are suffering from many of these challenges. So it's extremely important to be able to share these tools early on with the community so we get some feedback. And for some of you who haven't done field clinical trials, this is what my trials look like. And of course, we're sipping coffee and running these tools to really try to understand how they work. We get to share them, we publish this work, and at this point there are hundreds of designs out there that integrate very specific diagnostic tests on these sets of platforms. So this really becomes much more of a platform technology to build upon. I'm going to switch because I'm going to run out of time. Let me tell you maybe very quickly about another tool, because many of you work with molecules. We started thinking about this idea of how do you really bring the capacity to manipulate molecules to people around the world, both in the context of diagnostics, but also schools around the world. And this is work in progress. And my wife, again, getting back to toys, my wife gave me this object as a Christmas gift, and all of you probably know what this object is. I'm just going to play it for 1 second. All of you, how many of you have played with something like this? It's called a music box. The actual encoding of that music is in this strip of paper, and there's a little bit of a couple dollars of mechanics that converts it into sound. And I made a realization that if we can create music, how many of you have used these punch card tapes to program computers? Now, this is really telling your age. But it's very important because you realize the complexity of this strip really allows you to build and program many things. And we asked a very simple question: can I program chemistry? And the way we do this is we built these tools that are purely mechanical. There is a little chip, which is a microfluidic chip that couples to this. And instead of playing music, it really builds valves and pumps, 30 or so integrated pumps. And what we've been able to show, this is work that we're about to submit, that allows us with a single card and a single device, a completely mechanical device, we can run complex diagnostic assays to identify 5 different species of malaria. So this is really pushing molecular diagnostics in the field. And because of fundamental discoveries, for example, CRISPR-Cas-based systems, RPA, polymerase-based systems, these types of tools allow to bring that fundamental chemistry at very small volumes out to the field. Your assay or your protocol, this has a capacity to actually compete with many of your pipettes in its precision, but just like baseball cards, the card encodes all the complexity of the protocol. So, which is a huge challenge out in the field. The reason molecular diagnostics are not out there is because many errors, pipetting does not work out in the field to really be able to do something when you're trying to make decisions. Okay, in the last 10-15 minutes I want to talk about the last story which we've really spent the most time on, which is Foldscope. So let's go back in time. And starting from 1600s, look at the evolution of this beautiful tool. These are microscopes I put together. I should put some chronology, and choose your favorite one. My favorite one is coming very soon. It's right there. These are microscopes. I mean, they're also objects of art, almost. It's incredible precision, and if you follow some of the fields of science, every week there is a new instrument with a capacity and capability that comes out. All the way from thousands to millions of dollars built in these. And this very powerful tool allows us to see the secrets of nature and life. How do I do that outside the realm of conventional infrastructure? How do I do that for every single school kid in the world? We asked that question, and that led to what we call Foldscope that we published several years ago. The idea is we asked ourselves a constraint-based question. That given a single dollar, and I mean it, we actually put the constraint first and then came up with the design. What is the most powerful microscope we can build? We pushed the limits of physics, and we came up with these analytical solutions that allow us to understand high curvature micro-optics, and we built that in an instrument that's essentially origami. So just so for somebody who has not seen a Foldscope, a single sheet of paper that has a whole bunch of these parts, folds together in 5 to 10 minutes depending on your dexterity, and you get an instrument that's actually a fully functional microscope. We can get all the way to 2 micron resolution. In the lab, we've pushed with many new lenses all the way to 0.7 micron resolution for a price point of $1 for manufacturing. The reason it's made out of paper is because we can do flat manufacturing, and origami allows precision when you fold it. So now, what does it look like? And if I had more time, I will do in the very end data. But this is the type of data that I'm collecting, or communities are collecting around the world. This is a single ciliate that I'm yet to identify out in the field and I'm collecting this data using many cell phones that are around. It's very important when we built this tool philosophically that this had to work independently. So this does not require any phone or anything to use, but then if you have it, you get to capture data. That's individual cilia that you're watching. Now, what do you get to do? We use these tools for diagnostics, which is how we first started, and there's lots of groups around the world that have been using these tools independent of us to really do field work associated with this. This has also inspired us to build many new tools. So there is a new tool that I'm very excited about. I haven't talked about publicly about that tool, which is now an autonomous version of some of these tools. They cost us around $100 to make, but they allow us to really bring fluorescence microscopy and mosaic microscopy. This is a tool for being able to do diagnosis both for TB and malaria, but also to be able to do high throughput imaging, very much how you would do it for a tool that would cost traditionally $50,000 to build. But one of the things that I want to do is transition and really talk about what happens when you make a tool and what next steps do you take. This is what happens. You give people tool, and this is not a posed picture, and this is an aha moment captured on camera. That's the aha moment, and you don't want to know what some of these people are saying. Some of it is okay to hear, but not others. When we came up with this idea and we published a paper, I mean, I was very proud. This was the first paper from our lab. And then we asked, when you submit a paper, it comes online, you're very proud, and you look back and say nothing in the world actually changes the next day. And that's one of the challenges that we really have to face as scientists, is that eventually many ideas have to be absorbed in the community to really have their impact, and sometimes that takes a long time. And I had this notion that if we truly are true to our notion of frugal science, we decided to build in the lab initially 10,000, but then eventually 80,000 of these microscopes. I posted on my website. Anybody who wants a microscope from my own dime, I'm going to ship it to you. And I don't know if anybody in this crowd was phase 1. Did you ever write to me? Probably not. Okay. What that led is, first of all, it turned the lab into a manufacturing plant, but we really built a lot of robotics to be able to do this. This is what that robotics looks like. You'll see how high-tech we are. This is an instrument that we built that allows us to make a lens per second using, at the very end, you'll see a very important tool that you are used to. I don't know if some of you have identified what that tool actually is. These are glass lenses that we assemble, and it's going to show up in the very end. And this is the only reason we can really scale these sets of ideas. I want it to come. Okay, it doesn't matter. Right there, yes. Very important to build autonomous tools. One of the contexts is, this is also an evolution of ideas. This was the very first foldscope I built. You can recognize HomeLight. It's actually made out of a matchstick, and at this point, this is the current tool we have, and we keep changing and building capabilities. At this point, after that experiment and a couple more years, we have distributed and installed around 400,000 of these instruments around the world. They're being used in 140 countries. And one of the contexts that ends up happening, I did not realize that this is what I'm building. We're not building scientific tools, we're building communities. And that's a much more powerful idea than the tools, because the tools will come, but the communities are the most important. This is what it looks like. This is what it does to a child. This is my version of the story that David told you. This thing has volume, so. Science is very emotional. And one of the things that starts to happen is, from the tape, when you bring tools to people, they forget where they are. They are truly immersed in this microscopic world. Now the tools can couple, so you can collect live data. This is live copepods being imaged. You can connect them. And one of the things you get to do, you get to collect scientific data in the middle of nowhere. And you dive into this microscopic world. Now you'll see a little bit of microscopic monsters. I don't know if some of you have identified what this is. That's a maggot. know, the microscopic world is really alien because we have no intuition for it. And in life sciences, this is the most important fact, that unless you get intuition for these microscopic organisms, it's very hard to think. And I often think about the challenge that we place. This is ciliates in flower pots that my mother-in-law gave me that I didn't pay attention to. I don't know if some of you have identified what this object is. These are glass houses. These are diatoms, lime. And all this data is collected by community around the world. And I want to show one example and then I'll transition. This is the Death Star. And these things are real, you know, whether you believe in it or not, but you get to experience them firsthand. And that really is what creates this lifelong urging for mystery. You know, if I was to just tell you what all these things are, this is a one-eyed monster. I don't know how many of you have seen Monster Inc. It's inspired by this organism. A beating heart of a live animal that you can then put some drop of coffee and have the heart attack. Individual cells running around in a living organism that you get to see for yourself. This is actually a glass krill that's completely transparent. You're watching its brain, and for some reason it headbangs. This is data collected by a child in Panama, and one of the things that starts to happen with this is I got poison oak one time, and I got the wonderful opportunity to really see how this allergy spreads. You know, a single life emerged from single cells. This is starfish, first cell division. These are aphids drinking all the juices out of plant cells. And one of the things that I find the most wonderful, this is actually a new species of nematode that a group in Mexico discovered, and we're still trying to really identify and place. Spider eggs, this is where all your spiders come from, actually developing live in the field. This is when I don't do my dishes. So it's not about being in the Amazon. This is how ticks actually hang on to you. So although you don't like them, they're actually beautiful. Much of this data is collected on simple cell phones that exist around the world. And I'm not in my lab doing this, and the community members are not in the lab. This is actually on a little sailboat. So it really gives you a context of bringing science outside the community. And then I'm not going to do a demo right now. I might do it at the very end of the talk outside. But I want to share with you what is the social context of this. So here's a little clip that actually shows you the people engaged. Because I think if there was only one lesson to be taken, it's really about what is this community. This group is out in northeast India. This is Kaziranga, one of the last places where rhinos are found in India. Many of these people, when they came to this workshop, had guns because they are the rangers that protect the ecosystem. You already saw the kind of data that comes out of this. This is actually a fly that transmits leishmaniasis. This is from Panama. And one of the things you're going to see here is not just the diversity of things that people explore, but also the diversity of people. These are developing ants, favorite hydra, ciliates. This is Madagascar. We choose certain locations where we spend a lot of time. And here is a kid out in the street who for the first time realized I'm going to pick some mouse. This is blood from him actually being digested. These are kids in Madagascar. We have a big biodiversity discovery program. Tanzania, we're really focused on bringing sanitation and hygiene habits, teaching germ theory from scratch to be able to understand does that make behavioral changes. We have a big program with the government of India that's really trying to bring these tools to the most remote places in the country. Now this is one of the most heartbreaking examples. This is Syria, and this is a refugee camp in Lebanon where roughly 500,000 kids are not going to school. We're missing essentially an entire generation of people. Now, this is a high school, or school in the United States, and you're going to see the kid again that you've seen before. And one of the contexts that starts to happen with this is many of these people do things that we don't dictate. It's the ownership of what they do really belongs to them. You've seen that. What this gets to do is we connect them all on an online platform. So anybody who has access to internet gets to write their stories. So there are thousands and thousands of examples of projects, discoveries, and just curiosities that people have created that creates this network of teachers. How many of you are teachers? How many of you actually teach currently? So you realize this context that, you know, the biological world is both wonderful and terrifying because there's so much we don't know. But when you transition it to be able to share that, and not just share what we know, but share questions, that really creates a community. And this is what I'm most proud of, is the fact that here is a community where you can toss in an idea where everybody in our community is equal. We've been able to map 79 orders, and all of this data is freely and openly accessible at this site, microcosmos.foldscope.com. Now, let me switch to the social context. I'm going to take 2 minutes to just talk about this. We create tools and we create communities, but where we're going is a very simple vision, which is we want to make the world a more curious place. And the way we could do that is if you could compare this microscope with something like a pen or a pencil, what really happens to this world where 2 billion kids are carrying around these powerful tools, not just this, but many scientific tools in their pocket? I don't know the answer to that, but one of the things that I do know that we get a chance to engage these kids far more deeply in both the fascination and the challenges that we have in front of us. And this as a goal is really what I see, and I know that 2 billion number sounds far, we're roughly around 500,000 per drop in the ocean, but this is what we want to do, and that's why we sort of need your help. This community is remarkable, and if I had hours, I would spend 1 hour just telling you stories about, you know, here's a kid, and she actually discovered a species of ant in Madagascar, but she has no money to buy shoes, and then she relates this conversation with one of her grandmothers when she goes back and takes this tool back to her village in Madagascar. Here is a farmer in India who has spent his entire life growing a certain type of cotton. And for the very first time, he has incredible intuitive knowledge. He gets to actually see the pathogens. And we have a program in agriculture where we're teaching farmers to actually use these tools to really understand plant diseases. Here is an adventurer, a true explorer. This is Gurek, one of the youngest people on a sailboat to actually cross the Canadian Channel. He carries his chicken, Monique, and that chicken is observing the foldscope. And the purpose of this is he is one of our thousands of recruits who are sailors, who are actually exploring another ecosystem that you and I can't even dream of exploring as yet because we're not out there, and much of the life in the ocean we can't bring back to the lab at all. So we get to really do the kind of science with this data that we cannot do in the lab. And the way we do this is to really make sure that, and the hardest part of this project and implementation was how do we make sure that we are inclusive and we can maintain the diversity so that anybody who's curious is allowed to be a part of this community. And that's why that price point was very important. And then one of the things that ends up happening is there are thousands and thousands of projects that I don't have time to talk about. I want to show you 1 or 2 videos and something that's actually very relevant. If any of you speak languages other than English, we would love to have you engage in translating much of the instruction sets for these. So this is Hindi, but we have 60 or so languages covered at this point. I already talked about Syria, but let's take a few minutes to actually just watch these 2 videos. Because I want you to hear what one of the students has to say.
We are going to take slices.
Here's a teacher from Lebanon. Okay, one of the things that's happening is many of these kids go into second shift in the Lebanese school. And of course, many of them don't speak English.
أنا جيت من سوريا لأنه كان في عنا حرب. بدي أشوف شيء أنا ما بشوفه بالعين المجردة، بشوفه بس بالفولدسكوب، وبشوف سيل وول نيوكليوس cytoplasma membrane.
So, I think one of the things that I find remarkable is there's incredible people around the world who are truly voiceless. And this has nothing to do with looking far away. You could throw a stone around in our own neighborhoods and find kids who just have not had the chance to express both their emotions and their way of looking at the world. So one of the most important things that we really try to do is really figure out how do you empower them to engage in a platform where they have a voice. It's not about being right or wrong, but the fact that somebody is listening on the other end. And I'm going to skip many of these examples. This was from the Amazon rainforest. This is actually Tanzania.
And so important.
This is a group who runs an orphanage in rural India. And this single man, and I think what's so important about, of course, many people hear about Foldscope. This is Mo Pandirajan. He single-handedly trained 10,000 kids in this community in Tamil Nadu in India. And of course, I didn't know this until I met this person, and I had a realization that there are members in our communities, and many of you are teachers, so you realize what that means, is that once they have a spark of an idea, they really run with it. And then we really have absolutely no ownership of where it goes. This man runs life science galleries with many of his army of students that he's created in a place where you sell vegetables. So he has a view of this world. It's completely different from how I would think about it. And I'm going to leave you with this example. This actually comes from Kentucky. And let's just
Kentucky teenage science
second.
whiz is giving back to his community.
When 16-year-old Will Broomhead won a $1,500 science competition, well, he could have spent the money on himself. But as Joe Webb shows us, he decided to help hundreds of others.
How's everybody doing today?
It might look like your classroom.
Fantastic.
Mr. Farrell's 7th grade science class at Villa Madonna Academy today was part science, part origami.
Did you put it on the bottom or did you put the magnet on it?
Students
We
were
just
busy
did
putting
this with
together what
Alejandro
we
and
call
Kellyanne and a
Foldscopes,
couple of
portable,
postdocs here.
inexpensive,
in
but
several
high-quality
schools
microscopes.
in the neighborhood.
Works really well. Not only does it work with dry samples or wet samples, you could hook it up to your phone, see it through video on your phone.
You can see pond water, human blood, plant tissue at the cellular level by holding it up to the light without the huge investment of a traditional microscope.
So I think it's not about the
Foldscopes
microscope,
being
but I
assembled
want you to
today
hear
are
about
a gift from 16-year-old Will Broomhead. When his essay won PBS's Emperor Science Award last year, he got the chance to work with cancer researchers, plus he won a $1,500 prize.
When I got the stipend, the main purpose of it was to help you do your research that you wanted to with the doctors, and spending it on myself just didn't seem right.
So he bought Foldscopes for local science classes. Lots of Foldscopes.
The Villa students are not the only ones getting the Foldscopes. Will has donated 700 of these.
6 schools in northern Kentucky and Lexington are getting the Foldscopes. And
so this video goes on, but I want you to remember this. Here is a 16-year-old that empowered 700 others. And I think this is, I've never met Will. We've never had any correspondence. He himself thought about building a community. And actually, something that we didn't get to, he's a cancer survivor, and he said this really eloquently. He said, oh, I don't know whether I will become a good researcher or not, although I will try, but what about those 700? Maybe one of those 700 will actually excel, because we have absolutely no idea where talent comes from and why some of people in science are good. And I think that perception and that coming from a young individual and taking that time and effort, he went to every one of these 6 schools, he's been tracking these, he helps them document, training each one of these kids. So what I really find empowering is how do you really enable many others to take this in communities that matter the most. So I want to leave you with this. We can make microscopes, we can make scientific tools that will dazzle and excite. I can't manufacture mentors, that's you. How do we really bring and come out in a world where we have the chance to not only bring these powerful tools, but bring that network of mentorship to people? How do you really make sure that it does reach out to the voiceless? And one of the things that I'm most excited about and the experience that I got, which is a very emotional experience that I got a chance to have with Alejandro, Kellyanne, with Prep KC, is this idea that eventually in local communities, What I would like to see is, this is you, and this is the mixture of institutes involved. How do we really make sure that many of these tools, and not just this, but many other tools, will really get into the hands of people who will have the chance to transform their own lives? And this cannot happen from a single individual, although Alejandro has been really powerful in really bringing this idea here itself, and at least we've had this fascinating notion of thinking about how do you really engage a broader community. But this dialogue will not go anywhere unless we plug in you as a person. And again, the ownership belongs to you, and I am really curious to seeing where you take ideas and tools like this. So thank you so much for coming, and thank you so much for your time.